Cruz.
Yeah, good morning, everyone. Thanks, Jerome, for organizing this really exciting conference. I'm really excited to introduce both panelists this morning for me, because I guess this is like some of the sort of most exciting research in my world these days about how to change the world using applying some more fancy math and physics to economics and things like that. So,
by the way, I forgot to introduce you. So you have to introduce yourself. You have to do my job. So sorry.
Yeah, so I am not an economist. I am dabbling in economics these days, just kind of learning about it. My background is in math and physics, so it was theoretical physics and now kind of complexity science. I did my PhD at MIT and then a postdoc there. And now I'm actually working as an artificial intelligence machine learning scientist at General Motors for a bit to see how those tools. So I'll also be really interested to ask how what the panelist thinks like the potential of those tools are to applying economics, because I have some of my own opinions about that. But yeah, so I want to introduce the panelists. So Mark Kirstein is a postdoctoral fellow, I guess, right? At the London Mathematical Laboratory these days. He's working on kind of ergodicity economics, which is a field that says that, okay, ergodicity is this concept in math that says that, averages over ensembles and averages over time can be interchanged. And ergodicity economics kind of asks, well, is that actually true? Can we interchange those averages in economics in a lot of applications? And the answer is oftentimes no, but traditional kind of classical economics just didn't ask that question because they didn't have the concept of ergodicity back when it was invented. And so there's a lot of kind of exciting results coming out of like, oh, look at all these like traditional results in economics. And if we just do math correctly, if we just take this ergodicity assumption and clearly understand how that works, we get a lot of paradoxes that traditionally come up in economics get very simply explained, and you get a lot of kind of conclusions of like what are the best practices that align a lot more with our understanding of like morals and goods. And so I don't know, it's a very exciting field because it's yeah, it motivates people to act less selfishly and somehow more for the common good. So Mark is working on specifically applying that to expected discounted utility theory in face of some uncertainties, and had some papers even this year coming out in that. It seemed cool. And Lucio Bigero is a professor of economics and organizational science at University of L'Aquila. Is that right?
L'Aquila, correct. Yeah, correct. L'Aquila.
And so he works in applying kind of system science and cybernetics to economics and other fields, even kind of very far and wide, even including, he had some papers where he was co-authoring on cancer research and applying kind of systems thinking to cancer research, which I found very kind of exciting, just how broadly one can stray in research interests. Yeah, so specifically there's kind of network science in economics, agent-based modeling and the power that they have. And also I personally appreciated his kind of focus on some philosophy of science questions and epistemology that allows a fresh perspective on some of these traditional kind of entrenched methodologies and issues in economics and other fields. So I'll be excited to hear what exactly he talks about today, because there's such a broad scope that I have no expectations. So with that, I guess the panelists wanted to present a little bit first, and then we'll jump into questions.
Who wants to start?
It seems to me that you, Mark, had to present your work, and then if I well remember.
Yeah, just let me share my screen. Mm. Okay, you should see my slides now.
Yeah.
Does that work?
Yeah, it works.
Okay, yeah. Thank you very much. Hello from the north of Germany, actually. I'm happy to be here. I think, let me first of all thank Jerome for organizing this panel on very short notice. Also Pavel for the very nice introduction. I think it's due to my somehow outdated information that is online. I'm at the moment affiliated only with the Max Planck Institute for Mathematics in the Sciences in Leipzig. I used to be affiliated with the London Mathematical Laboratory, where a lot of these work on ergodicity economics has originated and is still coming from. And but at the moment I'm back in Germany, so to speak. Okay, so there are a lot of different aspects that are going to be explored and have been explored already during this conference. And what I will do with you in the next, let's say, 15 minutes and in the ongoing panel discussion is to explore the basic ideas of what ergodicity economics is actually all about. And Pavel already mentioned some of the keywords here. Of course, I can only do what is possible in 15 minutes. So if you would like to have a more thorough and comprehensive introduction to the field, please feel free to go to this website. You can just type it. It's MK-PhD-R1, and you can get a hand on my PhD thesis, where I discuss a lot of this stuff surrounding ergodicity and why economics has probably a hard time understanding what it is all about. But I warn you, this is PhD thesis length. If you want to have a more concise introduction, feel free to go to Ole Peter's survey or perspective article in Nature Physics, which for some reason has the same title. So it's actually pretty funny that ergodicity is a well-known topic in many sciences. Of course, in mathematics and in physics, where it originally came from an idea of Boltzmann when he thought about the origin of what would become statistical mechanics. And here in this nice article, it's even said, okay, ergodic theory plays a key role in so many fields, in biology and in chemistry. So it's actually a key task for me today to give you at least a motivation why ergodicity is also important beyond the natural sciences and an important concept to understand in economics. Some of the knowledge has already trickled down. So if you look at this tweet by Olivier Planchard, very influential economist, he says, okay, you can contribute a lot of the success, or let's say success, let me hyphen that, of macroeconomics. You can basically relegate it to an assumption of ergodicity. And whether or not this assumption is actually valid, this will be one of the tasks for me today. So maybe it's reasonable to understand what ergodicity, the mathematical part is. And I can tell you this is the only equation I will show, so please bear with me. So the first ingredient is here, what will become the left-hand side. This is a very familiar object for an economist, even if the notation might be unfamiliar. So this is simply a time average of, for example, an economic time series. So think about you're observing some process, some raw process, here denoted by X. It depends on T, so there is a realization of this process X over time. And you probably are not interested in kind of the raw prices. Maybe you are interested in, for example, the returns or some function of these raw prices. So this will be called f of xt. And then you follow this over time and you simply build an average. And what an ergodic theorem, which is everything that ergodic theory is all about, is actually saying, okay, this quantity, this time average, in some specific kind of convergence, converges to what we know as an expectation value, what in the language of ergodic theory would be called an ensemble average. The notation for this is these angular brackets, but it is simply an expectation value if you are more familiar with this notation. So feel free to always substitute the ensemble average whenever I say ensemble average by expectation value. So that's actually not something that, this is, I think, something that an economist can relate to. So you have time series averages that converge to some expectation value of this random quantity. Now, these kind of questions, or ergodic theory, can also be understood as the mathematical science of the asymptotic behavior of some kind of averages. And these kind of questions are actually relevant for us every day. For example, if we ask ourselves, what does it mean if we look in the weather forecast and it says 70% rain probability? Does it mean that, for example, if we are again here on the left-hand side, in 70% over this time experience, it will be raining? Or does it mean, for example, for 70% of the people or places on Earth or whatever on which we average, there will be rain? So what does it mean? So ergodicity helps you to think about it, but it also helps you to think about a more topical thing. For example, we are thinking a lot about the efficiency of vaccines. Here we have similar statements that are averaging statements. For example, what is the efficiency of a certain vaccine? What does it mean if it says 70%? Does it say, again, on the left-hand side here, does it mean it's 70% effective if I take it over the course of the time, and on 30% of the days it won't help me to protect me? Or does it mean it's 70% effective in 70% of the people that get it, for example? So that's not so clear. And here an understanding of ergodicity or of the meaning of averages helps us. Today, I will focus on a more specific meaning. So everything that comes now, you can boil down to that we are interested in the time average growth rate, which is this G bar here, or in the ensemble average growth rate, and whether these two are equal. So in the ergodic case, these two are equal or actually converge towards the expectation value. And of course, in the non-ergodic case, this will be an inequality. So let's jump into it by using a simple game, which is called Peter's coin toss by some people, because Ole Peters always used this to motivate the breaking of ergodicity, actually. So if I offer you a coin toss, which with equal probability lands either heads or tails, but if it lands heads, you get back 50% on top of what you have wagered. Or to express this differently, your initial wager is multiplied by 1.5. Or if it lands tails, you will lose 40% of what you have wagered. So your wager is multiplied by 0.6. Would you like to play this game or not? And in getting to an answer, what you actually have to deal with is to somehow cope with the randomness that is involved in this gamble. And of course, you can do this in many ways. And the common way in economics might be the following. For example, this is just an illustration of the randomness. You could think about tossing these coins, for example, once a minute. And then after 5 minutes, a possible realization of what would have happened to you if you would start with an initial wealth of 100 could look like this. But still, you know, it's random and you have to somehow cope with this randomness. So what to do with this? Well, you could say, okay, I toss this coin for some time, and but still there's still some randomness. You cannot really see, or maybe you cannot rely whether this is a reliable trend or not. But you could resolve to standard probability theory, which was developed in the 17th century, or the origins at least, and date back to Fermat and Pascal, what Pavel already mentioned. And what their idea was is to say, okay, in order to get a hand on this randomness, let's think about all the possible outcomes that can occur and average over them. And this kind of average is simply what we now call an expectation value, E of X. or an ensemble average in the language of ergodic theory, where it basically means you have an ensemble of possible outcomes, and then you average over the possible outcomes to get kind of a medium or a typical result, let's say, of this type of randomness. So let's do that strategy. So here I show you let's say 10 sequences of these random process of these possible coin tosses. You can imagine this as, for example, 10 people playing it, or 10 different copies of yourself playing it, or one copy of yourself imagining 10 times playing it, and or for 20 sequences, but still you cannot really see what is going on here. You need this averaging in order to get an idea of what is happening. So if we average, for example, over this 20 sequences, we might be seeing already somehow, let's say, sideward trend, but still some wiggles and up and down, so still pretty noisy. So let's average over 1,000 sequences. And so now what I'm doing here, I just take all of these sequences at a given moment in time, and I'm just averaging over them. And if I do this for 20 sequences or for 1,000 sequences, I see that this line is becoming more straighter and straighter, and I can do this for 1 million. And if I do it for 1 million times, then I basically don't see any randomness anymore. And I see behavior that would tell me, okay, maybe I should play this game, because on average, on ensemble average, if you may, we are winning in this game. So this is the first perspective that we can do. But now comes again our friend Ludwig Boltzmann at the end of the 19th century, where he asked the so-called ergodicity question. What does the ergodicity question mean? Well, it relates back to this ergodic theorem. Are these expectation values actually representative of what happens over time? So if these two left-hand side and the right-hand side of this earlier equation are equal, then we could substitute, and also Pavel mentioned this, then we can substitute one by the other. We can substitute the time average behavior with the ensemble average behavior. And you can express this in different ways. You can express it as the expectation value, but you can also think about these different realizations that I showed you as an average over systems versus an average in one system over time. So a different strategy to get a hold on this randomness would be to analyze this behavior as if we follow one trajectory for a very long time. So instead of taking the n to infinity limit, so the number of ensemble elements grows without bounds, here we say we follow one trajectory to infinity. So how does this look like? Again, here we have our initial the same series. This was, again, let me remind you, coin tosses, one coin toss per minute. What happens to an initial valve if we start with 100? And here it's for a time span of 60 minutes. So this is playing this game, this coin toss, for an hour. And we can then play this for a day. So we see, okay, looks kind of different because it's downward going. If we play it for a week, or if we play it even for a year, we have a similarity to the earlier picture, but in terms of that we have a straight line, so we cannot see any noise. Let's say we have extracted the signal from this random process, but the qualitative behavior of it is totally different. So on average, it looks like that a single individual, at least the one I have picked here, you may say, is losing. And this is what is called as by broken ergodicity or non-ergodicity. If we would compute the time average growth rate and the ensemble average growth rate for both of these perspectives, we would see, okay, here we are actually tracking the growth of the expectation value. And in this case, we are tracking the growth that almost any individual experiences over time. And you clearly see these two are not the same. And these non-ergodic behavior is actually a pretty generic feature of almost all living systems, of almost all growth dynamics, and so on and so forth. In order to quickly illustrate this, let me share a different.
Just to let you know, Mark, you're about 15 minutes in.
Yeah, I'm about to close. Thanks. So you should see now the multiplicative coin toss ergodicity breaking. Is this correct? Can you see this? Okay. So what I've done here already in terms of preparing this meeting, so I sampled these multiplicative coin tosses several times. So you see that almost all of these trajectories behave like this time average behaved that I just showed you. And in the blue line, you see this growth of the expectation value. So what we can see here, it might be a case that in economics is, for example, familiar if you're looking at the mean behavior, which is the blue line, and the median would be closer to the red line. So the median, if the median behaves differently than the mean, this might be simply a different way of expressing that some ergodicity is broken, even if you're not used to use the terminology of, let's say, time averages, ergodicity, and ensemble averages. So a lot of people may have seen this already, and you can resample. If you Google this observable HQ and multiplicative coin toss, you should easily find this. And if you take a new sample, you will see it only takes some time and any individual trajectory will follow this time average evolution. Okay, then let me quickly conclude, and before I give over to Lucio. So I think this broken ergodicity, as I said, is a fundamental feature of almost all living systems. You find this in many application fields. In the end, it is about a different embedding of randomness. You can embed randomness within the ensemble, but then you're always tracking the exceptional individual. So the exceptional rich that always has the, let's say, the positive coin toss over and over again. But ergodicity economics is all about asking this ergodicity question. Are these two perspectives the same? And if not, you should embed the randomness over time, because this is actually what corresponds to the experience of any single individual, be it a decision maker, a country over time, or whatever. In more technical terms, ergodicity economics is proposing a behavioral null model, which consists of the maximization of this long-term growth rate. And what you also can take away is that the mathematical quantity called expectation value may be one of the greatest misnomers in scientific history, because as you have seen, as an individual who plays this coin toss, the expectation value is actually not what you expect in the real world sense of expectation something. An interesting lesson to learn from, or to draw from this ergodicity economics work, and also from our more recent work on discounting and time lotteries, is that this long-term growth actually relies that you survive every single period, which gives some nice motivation, I think, and other perspective to think about stuff like climate economics, what you're actually maximizing there. And I think, for example, Hermann Daly framed or called the growth paradigm in a way as uneconomic growth. You can think of these ensemble average growth as uneconomic growth. Like in the coin toss example, following the standard methodology to tame randomness, you are lured into a behavior that is actually not optimal for you over time, because you're sure to go in ruin. And ergodicity economics helps you to ask the question, what is actually the identity of the mathematical quantities that we work with every day in and out? For example, you can simply, and this has actually led to a lot of confusion in the history of economics, you can simply look at the mathematical identity of the optimums of decision theory, and then you will characterize it as an arithmetic mean or as a geometric mean or whatever kind of mean. But it might be more instructive to also think about what is the mechanism that is lying behind it, behind this mathematical operation of averaging. What is the process there? And actually to think about it as a process. And then you are immediately at thinking about whether it's an ensemble or a time average. And let me stop here. I thank you for the attention. I'm looking forward to the discussion also with Lucio and with the rest of you guys. I think it might be impossible to ask all the questions, but feel free to contact me here. if you find this ergodicity stuff interesting, there will be an ergodicity economics conference next January, and I'm happy to see many of you. Let me thank you for now.
Great, thanks.